Negative 6. This is all you had to do yesterday. Look at an example. What? Go, darn you. Look at an example, and then use that for your problem. The example says if we're given a function, and here is that function, then if you plug 3 into that function for x, then you just literally plug it in. 3 times 3 minus 3 is 6. Okay, so if I plugged 3 in for x on that one, then I'm going to plug negative 2 in for x on this one. So that'd be 4 times negative 2 plus 2, which is negative 8, plus 2 is negative 6. I'm sorry? Just a little bit. But I'm actually a horse. When you're something pathetic, I pulled a muscle in my throat eating lunch yesterday, and it really hurt. You just get really out of shape. That's how you can do that. I was drinking, and all of a sudden I heard pop, and I was like, ah! And I didn't talk much the rest of the day. My 5th block went to the lab and just watched a video of a class I'd already recorded, and my 6th block learned from somebody else.
That's up.
It did. It hurt really bad. But thank you for your concern. But anyway, that's why I'm hoarse today. It doesn't hurt quite as bad, but yeah, a pulled throat muscle. Go figure. Now I won't be yelling at it. I won't be yelling at all today. What?
I didn't know you could pull a throat muscle.
Well, it was actually Mountain Dew, but yes,
Oh, well,
I was doing the dew. All right, you need to have out your worksheet from yesterday. We're going to go over that in detail. You will have a test. Ready to hate me? You ready? Wait for it, on Monday. And then you're going to have one, wait for it, on Wednesday. What? I'll tell you, the Wednesday one's nothing to stress about. We were just told by the school that we had to give a cumulative learning check. So it's going to be cumulative. It will not be as nearly as big a grade as one of our normal tests, but it will be a test format.
Mondays are real tests?
Monday's your test that we've been working on.
Can we take it Tuesday?
No, because Tuesday's shortened by AT time.
It'll be fine.
And we no.
No, it won't.
No, because that's when our other test is.
What about Thursday? Take it Thursday.
Thursday. Here's the thing. After this, I'm really done. After today, I'm really done teaching you for this unit. So I mean, I could give it tomorrow instead of Monday.
Can we do a review today?
Well, no, we're doing something else today.
Then why can't we? Well, yeah, we need to do.
But we can't review Friday, Monday, and Tuesday. That would just be a horrible waste of time. So, yeah, we're just going to do it Monday. I'll post the video. If you just don't want to look at it until Sunday night, whatever, that's fine. But we'll have a test Monday. Then we'll review for the test on Wednesday, Tuesday. And then we'll take the test on Wednesday. And if all goes according to plan, hopefully the rest of the week won't be too stressful
What will we
after
do
that.
the rest of the week? Next week.
Things that aren't too stressful.
So, I mean, alright, never mind.
Okay.
I'm done asking questions.
Okay. Moving on. Have out your worksheet from yesterday. All right, now we're going to go out of order because if I was going to teach via this worksheet, I would do them out of order. All right, now I don't have the exact page numbers written down, but I think I came around and showed everyone where these were in different sections yesterday at different times. These. I can determine a solution set for an equation. Find the solution set for the equation given the replacement set. Now, you want to write down these correct answers. I already graded your progress yesterday. You want to write down these correct answers as we do them because this is what you're going to have to study for this material.
So this is like a study guide?
Yes, this is the study guide for this portion. This isn't the only thing we've learned. In fact, it's like 1/3 of it, which is why we're going to have a full review tomorrow. But yeah, this is the study guide for that portion. Find the solution set for the equation. All you had to do here was plug in these coordinates and see which ones worked. See which ones actually made that thing equal. Now, let me show you an easier way to do it rather than just plugging in everything for x and everything for y and everything for x and everything for y. There's actually a much quicker way to do this. And let me show you that. You all need to have out a calculator, preferably a graphing calculator. If you do not have a graphing calculator, you need to come up and grab one of mine. I would say one of the light gray or yellow ones.
Wait, what's a graphing calculator?
one of these big fancy schmancy ones, like this. And you're welcome to use one of mine, yellow or light gray. You can't put a function into that. We're going to put a function into this. Now, like I said, you don't have to do it like this, but I think it's easiest like this. The yellow and light gray ones are the best. If you get a dark gray, those will work, but they're not quite as cool.
Oh, I got a dark gray.
Oh, that blue one's pretty good. That blue one's good. All right. You need to hit the Y equals button in the top left-hand corner. You should be looking at something like this. Now, what this does is this lets you put in an equation. As long as Y is solved for, yet another perk to solving for Y. As long as Y is solved for, we'll grab a different one. You can plug in the equation that it's equal to, and it'll give you every coordinate on that point. So, let's plug in 8x minus 5. 8x minus.
Where you X at?
X is the button right under mode.
Where's that at?
Second column.
I found it.
Second. It's like one of the top left buttons.
I found it.
It's got X, T.
It's on the green alphabet.
Yeah, next to the green alphabet. Now, before I hit anything, let me tell you what this is going to do. Would you agree that this is just a linear equation? What's the slope? What's the y-intercept? Yeah, it's going to graph that line for us. Now, when it says find the solution sets, all that means is, all that means is which of these points are on this line. So what we're going to do is we're going to graph this line, and then we're using just a quick variation of buttons, we're going to say, okay, well, what is -6 on this line? And rather than have to plug in -6 and -47 to see if they equal, the calculator will say, oh, at -6, y is bleh. And we can be like, oh, is it -47? If it is, that point's on the line. If it's not, then it's not. So that's what we're going to do. So, you should have it on your screen. Now hit graph. Ka-chow. It's top right button.
Mine does not look like that.
Well, that's just because your window is different. If yours doesn't look like this, hit the zoom button. Zoom, then go down to standard, and hit enter. That's going to graph from -10 to 10 in both directions, X and Y.
Mine still don't look
This one's stupid.
That's because...
Yeah.
See this like at home.
So,
Mine looks like that. Like when you got to really go to
Let me try this.
this.
No, hold on.
Shut up. My line looks like that though. I didn't see that, honey child.
It's actually that Siri.
And Chris could go up there and put it in the light.
Second.
And we're gonna press print.
Try it. There it goes. I don't know what was wrong with it, but there it goes. All right, now, everybody hit the trace button. It's the number right next to graph, trace. The trace button is going to tell us all kinds of different values on our line. Now, what we're going to plug in is -6. Type in -6, and it'll only work if you've already hit trace. And it will tell you the y value if you punch in that x value. It says, hey, if you take a minute. It says, if you punch in -6, what?
Mine's not doing that.
why don't you get different calculator?
Let me see it.
Said no.
Because this one's your work. Yes, it does. You said you didn't do it. Now, it says if this is your x value, then that's your y value.
I'll press enter.
Yes. It says if that's your x value, that's your y value. Is that the y value that this point has?
Error
No.
syntax.
No. Syntax. Did you actually graph, trace, -6? You must have actually hit -6 wrong. All right. So if that's not the point that matches this one, then that point is not on our line. So not that one. Now I want you to go through and punch in -3, -5, -4, and see which one has the correct y values.
I forgot how we done it now.
hit trace. You don't have to see, that's the beauty of doing it like this.
Pressing them in.
That's fine. That's the beauty of doing it like this, is you don't have to like punch it in every single time.
I just cleared all it's -5. Like,
just hit graph again and it's back. -5 works?
Yep.
Yeah.
Yes, it does. Is that the only one?
I have no idea.
Yes, it is. Well, if you keep pushing them in like this one, I pushed in -4. Did you push in -4? Did your graph go away?
Yes, I did. Don't worry.
Very good. Yeah, because it's -37, right? Which is not -42. It's
I'm so confused.
hit graph.
I did.
Then look at what you punched in again.
These calculators cost a bunch.
They do.
What do you mean?
it costs like $100 a piece.
What did,
Teachers, excuse this interruption. At this time, release the freshman with the last name A and B only to
are there questions about where we got that answer, -5? No, seriously, ask me if you've got them. Don't be embarrassed if you're having calculator troubles. That's something I need to know. And if you don't have a graphing calculator in front of you, shame on you, because I'm trying to show you easy ways to do this stuff. All right. Well, then try the second. Now, why can't we do that with the second one?
Because the wall's not by itself.
The y is not by itself. So you could just plug these numbers in, as you could in the last one, or you could solve for y and then do it in the calculator again. And that may seem like it's more trouble, but once you get used to these calculators, it's actually not going to be bad at all.
You can let us do this on the test.
Sure, you always have calculators to use on the tests. Well, not always, but most of the time. So, let's solve this thing for y, and then do it again. What do I need to do to solve this thing for y? Very good. Now, is 4 minus 4x 0? No. People still are doing that. Don't do that. It's just 4 minus 4x. Now what do I have to do? Divide by 2. So that's going to give me y equals, what is that, 2 minus 2x? Yeah. Now I have to take this off the board in order to use my calculator, but has everybody got that now, 2 minus 2x? Now, let's graph that thing. Discard. Y equals 2 minus 2x. Graph. Should look like that. Now let's trace these x values. Trace. -3. Enter. Nope. I hit the wrong thing. Hey, that one worked. Let's try -2. That one didn't work. Try -4. That one didn't work. And -1. That one didn't work. So -3/8 is the only one that worked. So the two answers to that I guess you just could have circled were negative, was it a -5? -5/45, -45, and -3/8 were the two that worked for those. Questions? Again, all this question's asking is which of these points actually lie on our line, and the easiest way to do it is just graph the dang line and say, hey calculator, is that point on the line? Yeah or no. Or you could just plug them in. That would work too. Questions? Alright, let's go on to the next slide. Solve the equation for the given domain. Hey, we're going to do this one the exact same way. Okay? Let's go punch that thing in the calculator. Now again, all this question is asking is, if here's 5 x values, find the 5 y values. That's what this question is asking. It's saying, if you have these x values in this line, what are your y values? And how would we find those? How would you find y values if you were given the x values? Rhymes with schmug them in.
Plug them in.
Just plug them in. Yeah. So what we're going to do is we are just going to plug them in, but we're going to let the calculator do the hard work. On y equals -x plus 3, -x plus 3. Then we're going to graph, trace, and we're going to let the calculator do the work. How about -5? Now I can't write on my board as I'm doing this, but you guys can write on your paper. -5, 8 is the first point. How about 0? Well, we know that's going to be 3. That's the y-intercept. How about 1, 2? How about 3, 0? And how about 4, negative 1? And then, just like that, you could have listed those as coordinates. Negative 5, comma, whatever it was, 0, comma 3, 1, comma, I don't remember what they were. But you just list them as coordinates, and that is the solution set, given that domain. Now this leads very well into what we're going to talk about next, which is functions. From what you read yesterday, what is the domain of a function? Yeah, it's just the x values. It's all the x values that are used for that particular function. In this one, those are the only x values. That's why they said for the given domain, meaning only for these x values. And the range is just the y values that you use. So what you just found, those 5 values, would be the range of this function. Domain is the x, range is the y. Questions? All right, let's move on. Next question we're going to tackle is numbers 15 and 16, because these are the last two that did not deal with functions, that just dealt with lines. Determine whether the equation is a linear equation. If so, write the equation in standard form. I got to be honest, when I first read this, I was not a huge fan of this question, just because you could technically solve that for y and it would look linear. But in the book, I saw several people find yesterday that they said if you have a component that has multiple variables in it, even if they are just x and y, if there are multiple variables on one single element, then no, it is not a linear equation. So, 15 from your book was no, not a linear equation, and the reasoning was that it had multiple variables in one term. Right here. You actually have to divide by 4x so that you could solve for y. But, it's because when you divided by 4x, it would be in the denominator, and we didn't talk about that. So there's a reason for it. But anyway, number 16. Now, are there any multiple variables on that one? No. Yeah, there's fractions, but they're just numbers. So I told you guys, what's the easiest way to get rid of fractions? Multiply by the common denominator. And what is a common denominator between 3 and 4? 12, yeah. So if we multiply everything by 12, that's going to be 12x divided by 4. What's 12 divided by 4? 3x equals 12 times 4 plus 2 times 12, which is 24y. 24 divided by 3 is what? 8. Very good. Now all it wants it in is standard form. Who remembers what standard form is? ax plus by equals c. Does it matter which one? Does it matter if we move the x or the y? Well, you have to put the x and y on the same side. Yeah, the number in front of the x has to be positive, which it already is. So let's move this one so that that'll stay positive. So that's very good, Jordan. So we're going to subtract 8y. And that's 3x minus 8y equals 48. And that is standard form. We actually did that a week or so ago, but it's a nice review anyway. So that's what you should have gotten for that one. All you had to do was put it in standard form by getting rid of the fractions and putting the x's and y's on one side and the number on the other. Questions? What questions are there thus far? All right, let's get into the stuff we haven't looked at yet, and that is function notation. Which relation is a function? Who remembers yesterday? In your book, it talks about, on these examples, it said this one was not a function, this one was. What was the only restriction about whether a relation is a function? Yeah, an x value cannot repeat. The whole thing about a function is that when you graph it, when you graph a function, it should be When you graph a function, it should be continuous from left to right. Like even if it's just points, you should have like point, 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 point. Now, where you're going to have a problem with a function is when you have 2 points right on top of each other, because then it's not moving left to right. You have 2 that are stacked, which kind of gives you misleading data. Now, here's the point of all this. Let me give you a real-world example of a function. If I said, let's mark the temperature at 8 a.m. every morning, right? So we're going to have, yesterday it was this temperature, today it was this temperature, tomorrow it's this temperature, blah, 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 right? But if I had 2 markings for yesterday, what does that mean? How could we have 2 temperatures at 8 a.m. in the morning on a certain day? It's impossible. Yeah, that's why functions, their only restriction that you had to look for was which one did not have a repeating x value. They all had a repeating x value, repeating x value, repeating x value, except for a. Which is why it was the function. That is the only thing that they really care about when it comes to functions is, does your data make sense? Now you can have a repeating y value. Look at our chart right here. What would it mean if we had a repeating y value? If they were all like...
Means the temperature was steady.
Yeah, exactly. It means the temperature was the same, but that's perfectly normal, isn't it? It would have been... So that's fine. You just can't have 2 temperatures in one day. That'd be nuts. So yeah, your y values could be the same all the way across, just not your x values. So there the answer was A. The next question basically asked you the exact same thing. It said, which relation is a function? They just didn't list the points in the same way. Which one does not have a repeating x value? Looks like A, 2 is repeating. Oop. -5 is repeating in C. +5 is repeating in B. Doesn't look like anything is repeating in D. So D is our answer. That one is the function. Questions on that? You're going to have questions on your tests that say, is this a function? And all you have to worry about is if an x value is repeating. When it gives you points, I mean. When it gives you points. All right. Moving on. I hate these I can statements. Express each relation as a graph and a mapping. Then determine the domain and range of your relation. Okay. Now the domain and range are actually the easiest part. Let's just do that first. The domain, the domain is just the x values written in numerical order. So that would be 2 and 3 for the first one. You don't have to write them more than once. Just 2 and 3. The range are the y values written in order. So it looks like -5, 1, 3, and 4. Now, before I go on, notice they're calling this a relation. Is this a function?
No.
Why not, Sam?
2 x values are the same.
That's right. Repeating x values. Problem. All right. Now, first thing they wanted to do was graph them. So 1, 2, 3, 1. 2, -5. It's down there-ish. 2, 4. And 3, 3. And you can see that this is not a function because you have points that are overlapping here and here. You have overlapping points, which is a problem. The reason they have you do the mapping, and now I always think it's easier to do the domain and range before the mapping because then the numbers you need to put in there are staring you in the face. Your x's are just your domain and your y's are just your range. The whole point of a mapping is every x value should only go to one y value. Now the y values can, like we said, repeat as many times as they want, but you should only have one line coming out of each x value. But that's not the case here, is it? We had, let's see, 3, 1. I'm looking at these points. 2, -5. Oop, there it is. 2, 4. And 3, 3. And this mapping shows that this can't be a function because these x values are going to multiple things. Again, that's the whole point of a mapping. I actually kind of think mappings are ridiculous because it's a whole lot of work for very little progress, but nonetheless, that's the point. And there is going to be a mapping or two on your test, so we'll do the next one too. Are there questions about where I got my domain, the range, the graph, or the map? Any of it? Okay. Now, I'm going to pause for a second to say the whole point of yesterday, I don't know if you're noticing, but these problems, I know they're new and you've never seen them, but I think we can agree there hasn't been a problem yet that's been like complex. Now, there may be things you didn't know to do yet, but there hasn't been anything here that's taken a whole long time or people are like, whoa, I'm so confused, that's so complicated. All of math can be broken down into simple terms like this. Even you get to calculus, as long as you keep up with it, every day when you learn something, it can be broken down in simple terms. And the best way to do that is to put it in your own words. You could have the best teacher in the world, you could have to deal with me, whatever. Regardless of who your teacher is, you're never going to fully understand something unless you can think about it in your own way. And if you're in here and you're struggling, I would strongly recommend that after a lesson, you look at the examples on your own and learn to put them in your own words. When I started teaching, I was teaching pre-calculus my first year. I hadn't taken pre-calculus in years. And it's not like riding a bike, you forget some of it. But every day I had to look down at the examples and be like, what did they do here? Oh, that's all they did? And almost every day, that's what it boiled down to. Oh, that's all they did? But I had to see it for myself to realize that's all they did. Yesterday was not about me just throwing you guys at it. It was about some of you, and I saw some of you make great strides, about realizing that when you look at the examples, it's just quick little light bulbs on most problems. It's not some big, complicated, horrible thing. It's just, oh, that's all they're doing. So anyway, hopefully you made that epiphany yesterday, or you had that epiphany. All right, number, I can't see what that number is, but number whatever it is. Same thing. Who can tell me the domain of that second problem?
3, 1.
Yeah, you always want to put it in numerical order. So 1 and 3. What about the range?
0. -4.
There you go.
2, 0.
And 5?
And that. All the
2,
fives?
5.
2 fives.
No, you only have to list them once. That's the point of the graphing and the mapping, is so that you can see them individually. But no, when you list the domain and range, you only have to list it once. Let's see. It's like, and kind of my reasoning for that is like, if they were to ask me what I had in this class, I wouldn't say I had a freshman. I'd just say, hey, I had freshman. That's like the range of this class. I would just say, hey, that's what I have, and they know it's in here, if that makes any sense. Is that a function? Somebody other than Sam? Let's see. Who am I going to call on? Christian. Is that a function?
No,
Why not?
because it's got more than one x value.
It's got x values that occur more than once. Yeah, exactly. So, graphing. You don't have to be perfect on these graphs. Lord knows I'm not perfect on these graphs. 3, -4. 1, -2. 3, 5. 3, 0. And 1, 5. 1, 5. There's the graph. The mapping. X, Y, 1 and 3. -4, -2, 0, and 5. All right, 3, -4. 1, -2. 3, 5. 3, 0. 1, 5. And there's our mapping. Any questions about where any of that came from? All right then, moving on. We're almost done, I think. Not too many left. I can write the inverse of a relation. Okay, express the relation shown in each table, mapping or graph or set of ordered pairs. Who we get to choose. Then write the inverse of the relation. Okay. This is probably the one thing that was probably the hardest thing to find yesterday. Who found this? Who found inverses in the book? What did you find?
It's like the opposite.
I showed them backwards.
Yeah, that's all an inverse is. Let me show you an example of that. For instance, an inverse just takes your coordinates and flips them. And if you're thinking, what on earth is the point of that? The point is, well, you're going to get into it more in Algebra 2 and pre-calculus, but what it does is it completely flips your function if you were to graph the points, and it's actually kind of cool. So I'll tell you what we're going to do is I'm going to graph number 10 because it gives us the option, table, mapping, or graph. And on the first one, I'm going to show you the inverse by graphing. So, and hopefully you'll kind of see how the points are like exact opposites of one another around a certain line. So first, the point 2, -1, the point 4, 6, 1, 2, 3, 4, 5, 6, the point 2, -6, 1, 2, 3, 4, 5, 6, and the point 4, 0, right here. Okay? Now, that's all you had to do before you do the inverse. But to help you see what an inverse does, I'm going to connect the dots. That way you'll be able to see how the shape kind of flips. If you connect the dots, which you did not have to do, it's going to look like that. Now when I do the inverse, let me change colors here. When I do the inverse, I'm just going to flip my coordinates. -1, 2, 6, 4, 2, -6, and 0, 4. Hold on, did I do all these right? -1, 2. Oh yeah, oops, my bad. I'm glad you caught that because like this doesn't look right. 2, 3, 4, 5, 6, -6, comma 2. That's right. Erase that point. Now look what happens if I connect my dots. You see how, if you kind of look at it with sideways, you see how they're like the same thing, just kind of flipped over? That's what inverses do. Now, what I'm about to show you, technically you probably won't need to know until Algebra 2, but inverse relations are symmetrical around the line y equals x, which isn't drawn very well right here. But that line y equals x, which you can easily graph because the slope is 1 and the y-intercept is 0, that is the line for which inverse functions are symmetrical with one another. So that's just kind of a neat little tidbit. Questions on that one? Basically just flip your coordinates. That's the whole thing about inverses. Number 11. I did graphing on the last one. Let's do mapping on this one. Actually, you know what? Yeah, no, I don't feel like doing mapping. Let's just do the list of coordinates. Let's see, what are my x values? Looks like they are -2, my coordinates. -2, -6, 0, 2, 5, 1, and what was that, 6, 5? Those are the coordinates straight from the graph, from this graph right here. If you were a little off on one of those points, I guess it's not a big deal as long as you were close on most of them. X first, Y second. Yeah, I did. That's actually the exact same mistake I made a second ago, Paige, when I was graphing.
Teachers, at this time, relay C through E to the gym, freshmen only.
Oh, tartar sauce.
Freshmen C through E to
Darn
the
it!
gym.
I didn't mean to erase that. Crikey! Somebody tell me what those points were. I accidentally erased them. Well, a little louder.
0, 2.
No, these. Just keep going.
5, 1.
Okay. Now, the inverse points, and I believe this is the last problem. The inverse points, just flip them. So that'd be -6, -2, 2, 0, 1, 5, and 5, 6. We're not going to bother with a mapping one. I don't think you'll have an inverse mapping on your test. That'd be very specific. That's it. Was there any other question we didn't get to on there? Oh, yes, there was. Oops. Oh, but okay. This was the DOM. Function notation. One of the biggest points of function notation is just so it makes it obvious for like That way they don't have to say, hey, if here's a function or an equation, plug in this number. The whole point of function notation is so that they don't have to use that in such long terms, they can just put it like this. They're like, hey, if your function is f, then plug in 4 for whatever the variable was. In this case, x. So plugging in 4 for x, that was 3 times 4 plus 2, which was 12 plus 2, 14? Yes, it was. Thank you. Welcome back. The second one, we're just plugging in -8 for x. Now, I know we've kind of just barely got into function notation, but if you're wondering what's the point of the f and the g and the h, nothing. Nothing. The whole reason that they even have those letters is because there are going to be problems in the future where you might need 5 functions at once. But so that they don't have to keep going back and saying, hey, it was the third one. Hey, it was the fourth one. They just label them F, G, H. That way they'd be like, hey, it was F. Hey, it was G. Hey, it was H.
It's the same line.
That's exactly the same thing as Y. Yeah. This is the exact same thing as Y equals, etc. But they put it like this so that you can have multiple in one problem without being like, wait, I thought Y equaled that. Wait, I thought Y equaled that. That way they're like, hey, these are specific different equations. We're just going to label this one F and that one G. This one, Ricky, this one Gerard, blah, blah, blah. They're just names. Yes?
Where did you get 14?
We plugged 4 in for the x, which gave me 3 times 4 plus 2, which was 12 plus 2, which is 14.
Well, what happens to the F?
It was substituted out. See, it's like, imagine I asked you to graph this line, right? Slope of 3, y-intercept of 2. And then I said, hey, if you graph that line, what's the y-coordinate at x equals 4? That's what that is asking. That's what that's saying. That's saying, hey, if here's a line, what's the function going to equal, or what's the y value, as Gerard pointed out, when x is 4? So we just plug it in. It's still there. We just substituted something in for it, just for one brief moment. Like this one. If we were to graph this, this would be some kind of parabola, some kind of bowl. And then they're going to say, hey, what's the y-coordinate if x is -8 on that graph? Well, we are near graphing this yet, but all you have to do is plug -8 in for the variable on that function. So that would be -8 squared plus 3 times -8 minus 5. So that's 64 minus 24, which is 40, minus 5 would give you 35. I think I did that right. Don't forget, a negative number squared is always going to be positive. So that's 64 minus 24 minus 5.
So basically, you just forget about the letter. Why'd you put?
Yeah, you just substitute out the letter. Every letter in the problem. What were you saying? Okay. That's actually the basis for this problem. And this was the last one. Just to reinforce that whole, hey, here's an equation and we can plug anything we want to into that equation, they're saying, we're not even going to give you just a number, we're going to throw you something crazy like 2a. Okay, well, we're going to evaluate this function at 2a. We're just going to plug 2a in for x.
So they substitute something else in for it.
Yeah.
So that's how you figure out what to plug into the other x value.
Yep. And if you're looking at that and thinking, what's the point of that? Well, let's say, now I can't think of a specific example. Well, let's say, hey, here's a line. You know what? We're kind of, for our application, whatever we're talking about, maybe pizza prices in Japan, I don't know. Let's say we have to double that slope. Well, we're going to substitute out, our current slope for something twice that, so we'll substitute in 2a for x. So, h of 2a is just going to be 3 times 2a minus 7. Whatever is right here, you're just going to plug into the function for whatever the variable was.
So why'd you keep the letter this time?
I didn't keep the x. The x was the original. I got rid of that. But I plugged in what it told me to plug in. I'm just a follower when it comes to math. It tells me to plug it in, I plug it in.
So you keep the letter, like the H? Or is it like just go with the 2A?
The h doesn't really have anything to do with the problem. The h is just the name of that particular function. It's like, hey, this is function Harriet. We're not actually going to use that. That's just the name of the function. That way later, let's say I wanted you to keep all these functions. I'd be like, hey, pull out Harriet. And you'd be like, oh yeah, that was 3x minus 7. Because that was just the name of it. The h doesn't do anything. But it's saying, hey, if we have a function Harriet with a variable of x, I can substitute anything in I want to for that x. In this case, I'm substituting in 2a for the x, which we're going to simplify. What's 3 times 2a? And then minus 7, and we're done. There's nothing else you can do with that. There might even be, there might even be problems that say like, hey, here's a function, plug in like x squared for every x. It might give you the same exact variable. But whatever is in these parentheses is what you're going to plug in for what's in those parentheses.
So keep the letter like the H.
Yes.
And just like kind of forget about it, just let it be.
Yes. Yes.
Could you divide by 8? I'm just asking. Could you divide by 8 both sides?
Well, what's on? Well, okay. Here's the biggest difference between function notation and equations. Like equations, y equals, you can do whatever you want to both sides, right? In function notation, at least until you get to like upper calculus, a long time from now, you're never going to like, this isn't something you're going to add to or divide by. That's kind of the beauty of function notation is you don't have to do things to both sides. That's saying this equals that, and again, this is just like the name of that, so you won't ever have to like add 7 or divide by 6 or anything like that. That's what it is. That's the beauty of functions, is that you don't have to do all that adding to both sides and multiplying. That's just what it is. It's already broken down for you.
And also, if you're looking for H, it would like say find H instead of find H2.
What do you mean find H?
Like, if it wasn't a function, they would say find, like, if it was finding a number, I mean a letter, of what letter?
You mean like H of H? What do you mean find H? Why did you say H specifically? Because that's what's right there?
Because if this wasn't a function, it would say find H instead of find H2.
Yes. Yes, I think I understand what you're saying. Yes. Function notation is no different than linear equations. It just puts them in a way that we can use more than one at once.
Do we have to keep the H, or is it like...
Yes. Again,
we
let
have to
me,
put it down?
yes, this equals H of 2a. Now, again,
You
let,
put all the other ones though, so I didn't know.
well, I didn't just because once you've dealt with a lot of them, oh darn it, I took the other one away. You get used to, just acknowledging that it's not going to change. You don't bother writing it every time. The worksheet's done, right? Let me quickly show you, and I'm not going to give you any problems over this. I just want you to see it. Let me quickly show you the whole point of functions. All right, we're going to have 3 different equations. Not in function notation yet.
What is that?
These are just 3 different functions. Okay, now, if I said, actually let me go even one more. If I said, plug in 2, you'd be like, plug in 2 to which one? I'd be like, oh, the second one. Plug in 3, which one? The third one. I would have to keep saying, I would have to tell you which one every time because, they're all looking the exact same. But instead of putting them equal to y, if I said this one is f of x, this one is g of x, this one is h of x, and this one is j of x, then I could say, hey, plug in 2 for h. That just means come to this function and plug in 2 for the x in that function. They're just names. Like, hey, plug in 3 for function j. That means you're coming down to j of x and plugging in 3 for x. The reason these x's are all the same is because that's the variable I use. They don't have to be x's. They could be f sub smiley face. If I was 2 smiley face minus 4, that's just your variable.
So you can have like an A of X?
Sure.
A of X?
You could have Gerard of smiley face. Let me show you what Gerard of smiley face would look like.